Hello everyone, welcome to my video. In this video, we will discuss work and energy. We have been talking about using Newton's second law for a while. The F equals to ma provides information about instantaneous relationship between force and particle movement, velocity and acceleration. In the previous chapter, we can integrate equations such as dv equals to ds over dt to find out what's happening along the path. There are two other types of integration we can do involving force variable. Number one, we can do force times displacement. This will give us work and energy. And we can also do force times time. This will give us impulse and momentum, which we'll discuss later in the chapter. Let's consider this crate being pushed by a constant force over distance s. If we multiply the force along its traveled distance s, we will get a new variable called work, or represented as the letter U. The work has SI unit in joules or Newton meter. In imperial units, it is feet pound. You can see I put a star here. Keep in mind, this unit combination, the pound-feet combination, will come up again later on when we do moment. The full definition of work is that only forces that are parallel to the path will do work. This means that forces that are perpendicular to the path will not do work, such as in this case, the gravity won't do work because it's perpendicular to S. Let's consider this crate again. This time it is being pushed by a constant force F at an angle over distance S. What's happening now? Well, recall that on the previous slide we said only force that are unparallel to the path will do work. For this force F, we can break it into x and y, or even just say the tangential and normal direction of the path, ft and fv. T is tangential, v is perpendicular, the normal. In this case, fv is the same direction as the weight, mg, so which do not do work. Only ft, the tangential force component, do work here. Now we can look at a more generalized scenario. From A to A prime, this equation actually comes from a vector product f times cosine alpha times ds. The alpha is the angle formed between force and distance. The more generic equation for work is du equals to the force vector dot the d position vector. If you remember the product of two vectors is a scalar, then yes, the work du is a scalar. Although the work is a scalar, it can either take positive or negative values. Positive work means the force and displacement are in the same direction, and the negative work means force and displacement are in the opposite direction. Then we have two special names for those forces, do work and those do not. Force that produce work, we call them active force. In this case, the Ft in the example is the active force. And for the force that does not do work or produce work, we call them reactive force. In that case, Fn and mg in the previous example, they do not do work. They are perpendicular to the traveling path. Now, let's welcome back our best friend, integration. Just kidding. If you have a constant force, nice, we will simply multiply the tangential force component with its traveled path, right? F times s, which is easy. But life is a bit more complicated than that. Oftentimes, you will have to do with non-constant f, or force is a function of time, or something else. This is where you need to do integration. There are three types of work we would really care about. They're work done by a constant external force, work done by a spring, and work done by gravity. In the next few slides, we will look at them one by one. Number one, work done by a constant external force. In this case, through integration, the constant will simply remain as it, and our equation is simplified to p cosine alpha and L. L is a traveling distance. If you look at this equation closely, you should be able to see that the only x component of the force P is going to do work. Right? P does positive work, and Py and gravity do not do work. The second scenario is work done by a spring. We'll spend a little bit more time and going a bit slower here. Think about a cart attached to a spring. Okay, there are two cases. When the spring is undeformed, the spring will always produce a force that go against the movement. Right? So from the rest, whether you stretch it or compress it, you will feel the push or stretch. And when the spring is deformed, the force direction and moving direction can be the same or the opposite. Most likely they are the same. So for example, the spring is pushed, is compressed here. Once I release, the spring will produce a force to push my hand away. So to describe the force produced by a spring, we will use the Hooke's law, which gives us F spring equals to negative K delta x, and delta x is calculated by x2 minus x1, the final position minus the initial position of the spring. And delta x is a deformed distance of the spring, deformed displacement of the spring. Okay, about this negative sign here, I want to remind you, don't force yourself to think the negative sign is about the moving or force direction. It's actually not that simple. Right? We will get confused easily if you do that. We'll talk about the built-in feature on the next slide and why this negative sign is mathematically making sense to us. Using the Hooke's law, F equals to negative Kx, from position 1 to position 2, right, either you're stretching or compressing, through integration, we can get the work done by spring is 1 over 2 times k times x1 squared minus x2 squared. Right? This is the equation on textbook. What you see here is they got rid of the negative sign, but they messed up the x1, x2 placement. So I don't really like how the textbook merged the negative sign into the bracket and messed up with x1, x2 position, because delta, by calculating the difference, should always be calculated and presented as final minus initial. So I like to use this one instead. The work done by a spring from position 1 to position 2 is negative 1 over 2 times k x2 squared minus x1 squared. Right? In this form, the negative sign in the spring force is preserved. So you know this energy equation came from F equals to negative kx. Right? And the difference is presented by x2 minus x1, well, x2 squared minus x1 squared, but the placement of x2 and x1 is preserved. Given this spring work equation, we can look at it more closely, and hopefully the negative sign will make sense to you after this slide. Let's say the spring is being pulled from rest at 0 centimeter to 2 centimeter. You will get a negative U122 or negative work done. This is because the spring has increased deformation, or say being stretched from rest, and the spring force is going against the motion. The spring does not want to be stretched. So the work produced is negative. Then, if we gently release the stretched spring from 2 centimeters back to its unstretched 0 centimeters, we will get a positive work from 1 to 2, or positive U1 to 2 value. This is because the spring has decreased its deformation, or say it's getting restored to its unstretched position, and the spring force is going with the motion. So the work produced by spring in this case is positive. Okay, just like I don't want you to go, I will do negative work on you to prevent you from leaving, but when you're coming, I'm going to welcome you by pulling you, doing positive work on you. Okay, either way, please understand the negative and positive part, like why spring is doing positive and negative work. Lastly, the work done by gravity. First thing first, gravity is treated as a constant here. So this is our assumption. Okay, when it's constant, it's much easier. If you understood the work-force relationship from the spring example on the previous slide, this will be much easier. The equation to calculate the work done by gravity is U from 1 to 2 is negative mg multiply the difference in height, y2 minus y1, or some textbook like to use h2 minus h1. Let's use a scenario to help with our understanding. Say you are raising a product from ground 0 centimeter to 2 centimeter, raise it above ground. The equation will give you a negative U1 negative work value. This means the gravity did negative work. With the increased height, gravity is going against the movement. It does negative work. Right? Very similar to the spring, right? It's go against you. On the other hand, if we put the object from 2 centimeter high back to the ground 0 centimeter, the equation will give you a positive U1 positive work value. This means the gravity did positive work during the drop. So the decreased height gravity is going with the movement. It does positive work. Okay? Thinking about a more specific example here, just like the spring, I don't want you to go, I give you negative work. Think about our daily life. When you are climbing up the floor, you feel exhausted easily, right? Because the gravity is going against you, right? Doing negative work on you, make you exhausted, make you tired. And when you're going down the floor, it is easier because gravity is going with you, helping you going down the floor, going faster, right? Doing positive work on you. However, gravity can also be treated as a non-constant, especially when we are dealing with space-related questions. In section 1.5, we derive this equation gme equals to gr squared. If you forgot it already, please review it in section 1.5. With non-constant gravity, the work equation now is like the g times r squared times m multiplied by 1 over r2 minus 1 over r1. Right? You can see the work for non-constant gravity is depending on the mass of the object and the distance between two objects. Right? I don't think I will be doing any particular example in this. Maybe we do, but we'll see. Okay, let me pause here for a bit to allow you to digest what was happening in the last few slides. We looked at 3 common scenarios we're interested in calculating work. The work done by a constant external force, the work done by a spring, and work done by gravity. Okay, so this equation, this equation, this equation are the 3 most important equations. When the work is done by a non-constant gravity, this little bit more nasty one will come into play. For the work done by spring and work done by gravity, pay attention to the negative sign here. The negative sign here exists for a reason. If you still cannot understand why the negative sign is here, go back to the previous 2 slides. Look at the example, right? The spring from 0 to 2, from 2 to 0. The gravity from 0 to 2, 2 to 0. Like, why are they positive? Why are they negative? Please take a moment to make sure you understand the negative sign here.